Hello everyone, my name is Diksha and I am from the Bodhi Academy. Today I am going to discuss one of the simple chapter from 12th standard chemistry, and that is general principles and processes of isolation of elements. In this chapter we are going to study about the process of isolation of elements, okay, from what are the processes that take place while isolating the elements and what are the principles behind them. So we already know the basic concept we have studied in our 10th standard about the minerals and ores, about the gang cube particles, about the metallurgy. So here we are going to study in more detail about the processes. First of all, we will study occurrence of elements. Occurrence of elements, where they occur, okay, in what form. So we can see in this table aluminium. Aluminium is obtained from the bauxite ore. Then kaolinite ore. Then iron is obtained from hematite, magnetite, siderite, iron pyrites, and these are the formulas, respective formulas. Then copper is obtained from copper pyrites, malachite, cuprite, copper glans, and zinc from zinc blende, calamine, and zincite. So here concentration of ores, removal of unwanted particles from the ore, it is called as a concentration, meaning ore we have so many unwanted particles, that is impurities which we want to remove, and that is called as concentration, dressing or benefaction, and it involves number of steps or processes. So here we will see one by one. So first of all we will talk about hydraulic washing. Now this is one of the method or way to carry out the concentration. So this is based on the differences in gravities of ore and the gangue particles, meaning when you have difference in the ore and the gangue particle, their gravities, then you can use hydraulic washing, and it is therefore a type of gravity separation. So it is based on the gravity basically. So what happened here is, in such process an upward stream of running water is used to wash the powdered ore, and lighter gangue particles are washed away and heavier ores are left behind. So this is how ores and impurities are this is how the gangue particles are separated from the ore. Next is magnetic separation, which is very important method, and this diagram as well is very important. So now this is based on magnetic properties of the ore components. So whenever you have magnetic properties difference, then you can use this method. If either the ore or the gangue is capable of being attracted by the magnetic field. So such separations are carried out in this case. So here what happens is the ground ore is carried out in a conveyor belt which passes over a magnetic roller. So here finely grounded ore is put, then with the roller it comes, and this is a magnetic roller which keeps the magnetic particles separately and non-magnetic particles separately. So they are collected in one container and magnetic particles are connected in another container. So this is how we can separate. Now this method is basically used in case of iron ores, okay, because they have traction towards the magnetic field. So that's why we can use this mostly in the case of iron ore. So iron ores means you should remember that we are talking about hematite, magnetite, because they are iron ores. Okay, so we can use hematite, magnetites in this case. Then next is froth flotation. Now this is a different method to carry out the same thing. So this method is used for removing gangue from sulfide ores. So you have to remember that froth flotation is used basically for sulfide ores, and in this process suspension of the powder is made with water, and to that two things are added. So what are those two things? Collectors and froth stabilizers. So here these two things are added. Now there are specific functions of these two components that we will see. So collectors, why we add collectors? Collectors, for example, pine oils or fatty acids or xanthates, they are added to enhance the non-wettability of the mineral particles, meaning it helps enhancing the non-wettability of the mineral particles. And then froth stabilizer is added to stabilize the froth, and these are the examples: cresol and aniline. Then what happens? The mineral particles, they become wet by oils, while the gangue particles became wet by water. And rotating paddle, this is a paddle which is shown, which it agitates the mixture and draws air in it. Okay, draws air in it, and then froth is formed. So this is the froth, mineral froth, which is shown here, and which carries the mineral particles, and froth is light and is skimmed off, and it is derived from the recovery of the ore particles. So this is how this is done. Now one thing we have to remember here is it is possible to separate two sulfide ores through this method. Okay, now how to do this? By adjusting the proportion of oil to water, or by using depressants. Now what are depressants? Now depressants will help, okay, in it selectively prevents zinc sulfide from coming to the froth, but allows lead sulfide to come with the froth. So this is used to separate two sulfide ores. So it will allow one sulfide ore to come in the come with the froth, and will deny other sulfide ore to come with the froth. So this is how the froth flotation process works. Then next is leaching. Now it is used if the ore is soluble in some suitable solvent. So first example is leaching of alumina from bauxite. And this is one of the important method. So here principal ore, now we know the aluminium ores, that is bauxite is the aluminium ore. Usually it contains silicon dioxide, iron oxide or titanium oxide. They are present as the impurities. So concentration is carried out by digesting the powdered ore in the concentrated solution, and this way aluminium oxide is leached out as a sodium aluminate. So this is a reaction which shows the process, and here aluminate in the solution is neutralized by passing carbon dioxide gas. So you need to remember the reaction and the process and which ores we use here. Then other examples is in the metallurgy of silver and gold, respective metal is leached with the dilute solution of sodium cyanide or potassium cyanide. So when you carry out the metallurgy of silver and gold, then the metal is leached with these two solution, that is NaCN or KCN. Then extraction of crude metal from the concentrated ore. So there are different steps which we carry out here. So let us start one by one. First step is conversion to oxide. So in that we follow certain processes. So first one is calcination. Now calcination, we came across to this term in 10th standard, two terms, calcination, roasting in metals and non-metals. So now what is calcination? Calcination involves heating when the volatile metal escapes, leaving behind the metal oxide. Now in simple words, calcination is the heating in limited supply of air. In this we can carry out these reactions, ferric oxide to give ferric to separate the hydrate, that is water molecule. Then zinc carbonate to give zinc oxide, and calcium carbonate, magnesium carbonate to separate the calcium oxide, magnesium oxide and carbon dioxide. Then next is roasting. Roasting is the process in which we heat in the regular supply of air or excess air in the furnace at a temperature below the melting point of the metal. So these three reactions shows the roasting process, that is zinc sulfide, lead sulfide and cuprous sulfide. Okay, then we will talk about the thermodynamic principles of metallurgy. So in this case, only you need to remember is when the value of delta G, that is Gibbs free energy, is negative, then reaction will proceed. Meaning if delta G is negative, then reaction is spontaneous, it will proceed. If delta S is positive, then increasing the temperature, the value of T delta S will increase and delta G will become negative. And if the reactants and products of two reactions put together in a system, then net delta G of the two possible reactions is negative. So overall reaction will occur. So this is how the thermodynamic is related to the metallurgy. Then we will talk about the applications of this process. Extraction of iron from its oxides. So oxides are ores of ions. After concentration through calcination or roasting, they are mixed with limestone and coke and fed into a blast furnace from its top. So oxide is reduced to a metal. So we can see here the oxide is reduced to the metal, and see, ferric oxide it is giving us iron Fe. Okay, it can be in solid or in liquid form. Then next important thing that we have is about the iron. Iron is obtained from blast furnace, contain 4% carbon and many impurities in smaller amount, and which is called as pig iron. So we need to know the different types of iron. So pig iron means which contains 4% of carbon and cast into a variety of shapes. Then cast iron is different from pig iron. It is made by melting pig iron with scrap iron and coke using hot air blast. So we need to know all the types of iron over here. Then wrought iron. Wrought iron is another form of iron. It is a purest form of commercial iron and prepared by a cast by oxidizing impurities in the river battery furnace. So this is how the cast wrought iron is made. Okay, so this is about the different forms of iron: cast iron, pig iron and wrought iron. Then next is extraction of copper from cuprous oxide. So cuprous oxide we can take and react with or heat it in the presence of air. Then we get cuprous oxide plus sulfur dioxide. Cuprous sulfide, when heated, it gives cuprous oxide and sulfur dioxide. And when it is further treated with carbon, cuprous oxide is treated with carbon to give copper and carbon monoxide. In actual process, the ore is heated in river battery furnace after mixing it with silica, and iron oxide slags as iron and silicate copper is produced in the form of copper matte. So it contains cuprous sulfide and ferric sulfide. So it gives us the slag. So copper matte is then charged into silica lined converter. Okay, then these are the reactions which takes place when we take iron sulfur, ferrous sulfide, ferric oxide and cuprous sulfide and cuprous oxide. Then extraction of zinc from zinc oxide. Zinc oxide, when treated again with carbon, it gives zinc. Okay, so reduction takes place here in presence of coke and 1673 Kelvin. Then electrochemical principles of metallurgy. Now this equation we already seen in electrochemistry chapter, that is delta G naught is equal to minus E minus NF E naught of cell, and this is a oxidation redox reaction which takes place. Now this process is very important, the diagram and the process, which is known as Hall-Héroult process. Okay, now this process is used in metallurgy of aluminium, the aluminium oxide. Okay, to obtain aluminium from aluminium oxide, this process is used. So aluminium oxide is mixed with sodium aluminium fluoride or calcium fluoride, which lowers the melting point of the mix and brings conductivity. So here carbon acts as a cathode and graphite acts as a anode. So overall reaction is shown here. Aluminium oxide reacts with carbon to give aluminium and carbon dioxide. So electrolysis takes place here, and at cathode we have this reaction and anode we have this reaction which shows. Now these two reactions are equally important along with the diagram over here. Okay. Then copper from low grade ores. Copper is extracted from hydrometallurgy. Okay, from low grade ore it is leached out using acid or bacteria, and this is a reaction which shows copper when treated with hydrogen. Hydrometallurgy means involving water, so hydrogen, it gives copper and H plus ions. Okay, then we will talk about refining process. So in refining we have different steps or the processes. So distillation, liquation, electrolysis, zone refining, vapor phase refining and chromatographic method. So distillation, this is a very useful for low boiling metals like zinc and mercury. Impure metal is evaporated to obtain the pure metal as distillate. So this is very important. Then liquation in which low melting metal like tin, it can be made to flow on a sloping surface. So in this way it is separated from higher melting impurities. Electrolytic refining, now this part is very important about copper refining. Copper is refined using electrolytic method, and anodes are of impure copper and pure copper strips are taken as a cathode. So here this is a reaction which takes place at anode, and this reaction takes place at cathode, and impurities that deposit as anode mud which contains antimony, selenium, tellurium, silver, gold, platinum. So this is one of the important thing you have to remember here, which impurities we get here. Then zone refining, this is very important in terms of exam because they ask diagram or principle or examples, anything from that. So the principle of zone refining is what? So the principle is based on, principle tells that impurities are more soluble in the melt than in the solid state of the metal. So in melt state they will be more soluble than in the solid state of the metal. So here what happens, a circular mobile heater is fixed at one end of the rod of the impure metal. Okay, so one end of the rod, this mobile heater is fixed. Then molten zone moves along with the heater, which is moved forward, and as the heater moves, the pure metal crystallizes out of the melt and impurities pass on to the adjacent molten zone. This is how this zone refining works. And then it is repeated several times and heater is moved in the same direction. Okay, then here this method is very useful in producing semiconductor and other metals of very high purity. For example, germanium, silicon, boron, gallium and indium. Then next is vapor phase refining. In vapor phase refining, the metal is converted into the volatile component and collected elsewhere. So here condition is metal should form a volatile compound with an available reagent, and volatile compound should be easily decomposable. Next very important reaction is Mond's process for refining nickel. So here nickel is heated in a stream of carbon monoxide to form a volatile complex, that is nickel tetracarbonyl. This is a nickel tetracarbonyl, which is then further heated at 450 to 470 Kelvin to get the pure nickel and carbon monoxide. This is impure and this is pure. Next is Van Arkel method for refining zirconium and titanium. Now this method is used specifically for zirconium and titanium only. So here the oxygen and nitrogen present in the form of impurity is removed from this particular metal ores. Then chromatographic methods. Now this method is based on component that different components mixture are differently adsorbed on an adsorbent. So it is put in the liquid or gaseous medium, it is moved to the adsorbent, and different components are adsorbed at different levels of the column. This is how it looks. Now the example here shown is of column chromatography. It is used for the purification of elements which are available in minute quantities, and the impurities are not very different in the chemical properties. So this chromatographic method is used to separate. Okay, so with this we finish our chapter Principles of Isolation Extraction. So this chapter is important and it is simple to understand, and it is important because of its diagrams, mostly diagrams from magnetic separation, then froth flotation, zone refining, Hall-Hérold process. These 4 diagrams are very important from this chapter, along with the small points which are about their processes, then applications, uses, then ores. So these are important points from this chapter. Okay, so with this we finish this chapter. So I will come with the next chapter in the next video. Thank you.